In this video, we want to prove this scalar triple product identity, and in fact it takes several more forms, as we'll see in a few moments. Now, to prove this, let's consider what happens now when we take the cross product of two vectors. Here, of course, we have A cross B. That gives us a vector. Then we're going to hit the dot product of that with vector C. That will give us a scalar quantity. And we say that's the same thing as if we took B cross C, then took that vector and the dot product with vector A. It'll give us the same scalar quantity. Now, how do we express A cross B in determinant form? Remember how that goes. We would have A1, A2, its different components, and the components followed by the components of the B vector. And then up on top we write the unit vectors. And that determinant equals A cross B. And the order is important. We have A, then B, so we have row A, then row B, and at the very top, the unit vectors I, J, and K. And this gives us a vector. To see what expression it has, we can find out by expanding this using minors. So starting with I, then we cover up the first row and the first column, and we have this 2 by 2 determinant, A2, B2, A3, B3. And this is times the I unit vector. A2, B2, A3, B3. And then we expand across, let's say, the top row, so we'll have minus J. And then when we cover up the first row and the second column, we will have A1, B1, A3, B3. That is times the unit vector J. And then here we will have for the unit vector K, A1, B1, A2, B2. So this is A cross B. And if we had actual numbers in here, then we could take the determinant to find the coefficient of I, and the same for J and the same for K. What we want to do is take the dot product of this with vector C. So here we're going to hit the dot product, and we can write vector C in component form, C1I, like this. Now when we take this dot product, there is vector C in component form. We'll have I dot I, that's 1. So we'll have C1 times this. We don't need this anymore. Then J dot J, that's 1. Of course, all these are mutually perpendicular, so J cross K is 0, or J dot K is 0. But J dot J is 1. So we'll have C2 times this, and then K dot K is 1, so we'll have C3 times this. So when we take C dot A cross B, we have this expression. Well, back in our original determinant for the cross product of A and B, this 2 by 2 determinant was multiplied by the unit vector I. Now it's being multiplied by C1. This originally was being multiplied by J, the J unit vector. Now it's being multiplied by C2. That originally is multiplied by the K unit vector. Now it's being multiplied by C3. So this expression would be the same as this determinant, with C1, C2, C3 across the top, followed by A1, A2, A3, B1, B2, and B3. So this determinant, that is C dot A cross B. So here is the scalar triple product written in determinant form. And notice the pattern. C is the vector that we're going to hit the dot product with. So its components are written on the very top row. They're the cross product of A cross B. So the second row is the components of A. The last row, the components of vector B. Now, what happens if we have then, just looking at this general pattern, suppose that we had the determinant like this. Suppose A was written across, the A components were written across the top. So we have A1, A2, A3, and then C1, C2, C3. If the determinant had this pattern, all we did was put A on top and have the C underneath, the C components. Here are the A components. But if we follow the same pattern, then this would be A dot C cross B. Following the same pattern between this scalar triple product and this determinant. Now, suppose that we left the A components on top, but we switched these two rows around. So we would have A1, A2, A3, then B1, followed by the C components. And again, if we follow the same pattern, that would be the vector A dot B cross C. Now, let's remember the rules of determinants, though. This determinant was derived from this one by doing a row change, a single row change. And when you do that kind of an operation on a determinant, that changes the sign of the determinant. If there's an odd number of row changes or column changes, that changes the sign of the determinant. Well, the determinant here is this. This determinant, where we have a sign change, is this. So what that means is that A dot C cross B is the negative of this. Now what about here? Well, here we had two row changes. To go from here to here, we shuffled two rows around. That's an even number, so this determinant has the same sign as this determinant. It'll have the same absolute quantity. If this had say a value of 10, this would have minus 10, and this would be back to having plus 10. The only thing that changes when you move these rows around, or the columns, is the sign of the determinant. If it's an odd number of changes, the numerical number is the same, but it'll have a negative sign compared to that determinant. Here, there is no sign change. this is an even number of changes in the rows. So that means then that this, which is this determinant, equals this, which is this determinant. So what we have is, starting here, C dot A cross B equals minus A dot C cross B. But it equals A dot B cross C. And this is the equation that we wanted to prove from up here. Now, I have a few moments left. There's a way that we can conveniently express all of this information and more. By doing it like this, A dot B cross C. We can write that in abbreviated form like this. A, B, C. That is A dot B cross C. Now this would be equal to B, C, A. That is B dot C cross A. And it's also equal to C, A, B. We have this form written right here. This is B cross C dot A. And the reason why this is true, to go from here to here, we shuffled these letters twice. We had B, A, C, and then we moved this over. So that's 2 BCA. That's an even number. There's no sign change in the determinant. So this and this are the same. Likewise, this is the same. Move it over once, move it over twice. So that's a very simple way of remembering the different identities of the scalar triple product. And likewise, this would equal minus A, C, B. We shuffled the letters one time, which means that we'd be changing one row in a determinant, change the sign of the determinant. Or this would equal minus B, AC. Again, one change, one is an odd number, or this would equal minus C, B, A. Where here, this would be a row change of 3. We start here, 1, 2 for C, A, B. That was 2 shuffles of the numbers. Now for B, A, that's 3. 3 is an odd number. The sign of the determinant becomes a negative compared to this. So this is how we can remember all of the possible scalar product identities, realizing, of course, that this is A dot B cross C, and that expression holds the same all the way across here. Remember it like that, then, and this is a real simple device for remembering something that otherwise might seem complicated. Okay, in the next video, we'll try and look at the curl operation, and the playlist for the vector series analysis is at the website digital-university.org. The first page is under construction, but the playlist for all the videos is there at the website.